Okay, so we've already done chi-square testing for goodness of fit with one population, chi-square test of independence again for one population. Today we are doing chi-square testing of homogeneity for multiple populations. That is the big change from the other two types of chi-square tests to today. So the chi-square test for homogeneity allows the observer to test if the populations within a two-way table are the same within multiple random samples or multiple groups within an experiment. That is the big change. You have multiple samples. So anytime you see a two-way table and you know that it's related to multiple samples, that tells you it is a chi-square test of homogeneity. Our null hypothesis is that there is no difference between the true distribution of a variable for several populations, while our alternative is that there is a difference. And again, we will find a chi-squared value, compare that to a p-value, and determine if we will reject or fail to reject our null. Another way to say these sometimes is to say that all of the populations are the same for a given variable versus some of the populations are different. We can't just say that one is different, because if one is different, then at least another one is different. So to not have to worry about how many there are, we just say either all of them are the same or all of them are different. So look at the next question on your homework. I believe it's number 5 in that same packet. No, wait, come back. Not number 5 yet. Real quick, conditions. The conditions are dominantly the same: random, expected counts, and independence. But the biggest change is that for random, it comes from random samples or groups in a randomized experiment. That is the big change. If there's more than one group or more than one sample, it is a chi-square test of homogeneity. And so our big idea is that we have multiple populations at stake. So the next question that we have on our homework, again, I think it's number 5, but go ahead and pause the video, read the question. Basically, we're looking at the opinions of consumers versus dentists on how they feel about advertising. So because I have a population or a sample of consumers and a sample of dentists, they are not the same populations. So that tells me right there that I'm going to do a chi-square test of homogeneity if my conditions are met. So we are trying to find out if the authors of the article are interested in determining whether the two groups differ in their attitudes towards advertising. Our null would be that they have the same opinion. Our alternative would be that their opinion is different. So we're doing a chi-square test of homogeneity. Again, the opinions of consumers and dentists are the same for the null. Our alternative is that they are different. We don't know how different. We don't care. We just know that one of them is the same, one of them is different. So the next thing I want to do is to do my expected counts just like we did in the past. Let me go back to the actual table. So just like we did the expected counts for the previous video on test of independence, I'm going to look at my row totals compared or times my column total divided by my grand total. And that would give me the expected count for this box right here. And I would repeat this process for all of the boxes. Yes, all of the boxes. You're going to have to do that. So let's pretend that you already did. So our expected counts would look like this. Again, you can write these in the table next to the ones you already found. These are rounded to 1 decimal place. Sometimes we do 2. 1 is okay as long as you don't round to a whole number. So I look at my expected counts. The smallest one I see is 14, so that tells me that I have enough information, or my sample is large enough to do a chi-squared test. So I'm going to go ahead and continue to see what other conditions are met to make sure I can do my chi-squared test of homogeneity. So I'm given that the table is from 2 independent random samples. I had, remember, the sample of dentists and the sample of consumers, so I have 2 different samples. The sample is large enough since our expected counts are greater than 5, so we can use chi-square procedures. And we are also going to infer that the populations are at least 1240 for consumers and dentists to guarantee independence. So at this point, I'm going to go ahead and calculate my chi-squared value. It is the same process we've done before. Observed minus expected divided by expected. Here's kind of 2 tables, or the 2 tables put together. Again, you might have these all on one table, and that's fine. So we're going to follow the same process we've done before. First one right here, here's the second one, and then we'll, the last one. Calculate this by hand. Someone came up with a good idea of putting observed in list 1, expected in list 2, and then in list 3 in your calculator, list 1 minus list 2, and then in list 4, to do list 3 squared, and that's totally fine. And you can also go to list 5 and then do list, what would that be, list 4 divided by list 1, I'm sorry, list 4 divided by list 2. Whichever your expected counts is would be what's on the bottom of your fraction. So either way, somehow figure out your chi-squared. You can do it by hand, all on your home screen, or you can use your lists. Either one is fine, but your chi-squared is 84.5. That seems kind of high, but let's talk about our degrees of freedom. The degrees of freedom will work the same way it did for a test of independence. I have 2 rows, and I have 1, 2, 3, 4, 5 columns. So I'm going to say that my degrees of freedom are going to be 2 minus 1 rows times, what did I say, 5 minus 1 columns. So I will have 4 degrees of freedom. 2 minus 1 times 5 minus 1 is 4. So 4 degrees of freedom, chi-squared of 84.5. I look at my table. Let's see. And did they give us an alpha? If not, we're going to assume 0.05. I don't see an alpha in the problem, so we will assume an alpha of 0.05. So I find that my p-value, again, it's going to be so small because chi-squared of 84.5 is somewhere in that direction. It's so tiny that it's basically 0. So if that's the case, it's guaranteed to be less than your alpha of 0.05. So we are going to reject our null hypothesis. It's the p-value is less than alpha. There's enough evidence to believe the opinions of consumers is different than the opinions of dentists. So this is how you do a chi-squared test if you have multiple populations. If you have one population, you would go back and do a test of independence. But here we have multiple populations, so it was the test of homogeneity. Let's kind of do a quick summary of all of our tests. The first test we talked about was for goodness of fit. This was the day we did the M&M activity. Okay, we had one sample of M&Ms. We are just looking at the population of M&Ms. So we had one sample with multiple categories, and those categories were the colors. So we are comparing the distribution of a variable to what is expected, and you are given either some kind of percentage or what's equally likely, or that they are all equally likely. This one is just like the M&M situation. Number 3 on your worksheet is one of these situations. We were talking about whether the die was fair, because if it's fair, each roll should be equally as likely to occur as the next roll. If you wanted to do a chi-square test for homogeneity, this is for multiple populations. You have a single variable, but multiple populations within that variable. This is the dentist versus consumers situation. We are talking about whether or not they agree or disagree to like advertising, but we're looking at consumers versus dentists. So because I have 2 populations, that's why I'm going to do a test of homogeneity. If I had only one population, but I had multiple variables, a good example here would be the deployed versus not deployed and the cause of death. So this is a situation where it's one population, but I'm trying to find out if there's an association within those 2, within the variables and the population. So again, goodness of it, one population. Independence or association, one population. Chi-square test for homogeneity is at least 2 or more populations. Okay, so that's how you can compare all 3 of them together. As always, if you have questions, please let me know. But that's the end of our notes. Go ahead and work through as many as you can in that packet that I gave you, and we'll do some of them in class on Monday.